When an AI writes a bad sentence, it puts characters on a screen. When an AI controlling a robotic arm fails, it violently swings a massive payload across a crowded factory floor. Governing generative AI has largely focused on information risk. An incorrect output in a text model exposes an organization to compliance violations, legal liability, or misinformation. Robotics introduces kinetic risk. A logic error becomes physical force, moving mass through space and creating immediate danger to life and property. Standard safety protocols for text models rely on post-generation monitoring. You review the output and filter the error. In a kinetic environment, this latency is fatal. You cannot undo a physical collision once the motion has begun. VORTIQ-X is engineering a robotics assurance layer to solve this problem. It sits directly between the autonomous decision-making compute and the physical actuators that move the hardware. Because kinetic actions are permanent, safety protocols must occur entirely in the milliseconds before the hardware moves. Governance must shift to strict pre-actuation validation. In standard software, the default safety response to high cognitive uncertainty is to hedge or throttle the output. If the model isn't sure, it performs the action with less intensity. Let's trace what happens when that logic is applied directly to a robotic pipeline. A move command leaves the autonomous engine, hits an uncertainty filter, and because the AI confidence is low, the filter cuts the power output in half before reaching the actuator. Imagine a bipedal humanoid navigating uneven ground. The cognitive model detects shifting gravel, and its certainty drops. If the system responds by throttling torque, the ankle joints lose the rigidity required to balance. The robot physically buckles under its own weight. Consider a robotic arm actuating a heavy industrial safety tool. The system encounters an anomaly and hesitates, limiting the force applied to the tool's trigger mechanism. Pulling a heavy mechanical trigger more slowly does not make the action safer. A half-engaged mechanism can jam or fail to lock, creating a secondary hazard that a fast, decisive actuation would have avoided. Treating all robotic actions through a uniform uncertainty lens creates a safety hazard. Kinetic physics requires a governance model that differentiates between types of movement. To fix this, VORTIQ-X governance middleware bridges the gap between decision engine and physical actuators. Deterministic action tier mounting splits commands into 3 distinct pathways. The first pathway, for reflexive actions, bypasses cognitive uncertainty filters to maintain physical integrity. Operations like dynamic balance and posture must execute without being throttled. A humanoid must maintain ankle rigidity. The second pathway governs task actions, routing them through physical boundary limits. Grasping and lifting can tolerate force reduction. If unsure of a box's weight, limiting maximum lifting force is a valid safety response. The third pathway captures unknown or consequential actions, hitting a hard wall. Any action outside pre-mapped registries or carrying ethical consequences defaults to a fail-closed state. These commands are blocked until they receive explicit human authorization. Deterministic routing strongly hardgates dangerous actions, while seamlessly allowing the high-frequency reflexive loops required to keep the physical machine operational. For commands on the task and unknown pathways, VORTIQ-X requires clearing 4 sequential gates before actuation. The first node checks locked action registries. Nodes 2 and 3 verify telemetry freshness and OT sensor health. The system confirms physical reality to ensure AI isn't moving mass in a non-existent environment. The fourth node runs simulation validation. Commands failing any gate are immediately dumped into an isolated emergency stop bin. This pipeline ensures strict alignment between the AI's intent, the robot's physical capabilities, and the actual state of the environment. The final node is pre-actuation evidence sealing. Once a command clears the pipeline, it receives a cryptographic stamp, finally turning the actuator pathway green. This enforces a foundational rule. 0 commands reach a physical actuator without verifiable, cryptographically sealed governance evidence attached. This generates an immutable, tamper-evident record detailing the exact logic behind every allowed, denied, or escalated action. While this pipeline creates a robust runtime safeguard, deploying this assurance layer does not constitute formal robotics certification on its own. Formal certification requires independent third-party assessment, separate validation of the physical hardware, and adherence to sector-specific safety processes. In an era where AI decisions instantly become physical motion, relying on post-generation filtering is simply impossible. A fail-closed, deterministic middleware layer is the required engineering foundation for trustworthy autonomous systems.